Hey again, guys. Well, thanks for coming back again. And I want to talk about what is a dipole moment in chemistry? What does it mean to be a polar molecule? I don't know. Let's look at some things, some examples. What if chlorine and chlorine, two chlorine atoms, were to enter into a bond? Would they be sharing electrons evenly or unevenly or transferring electrons? If you've been doing any reading at all, you know that two chlorine atoms are evenly matched in electronegativity, so they would perfectly share to make a pure covalent or non-polar covalent bond. On the other hand, carbon and oxygen are not balanced electronegatively. Electronegatively, I made that up. Okay, so oxygen is stronger at pulling electrons towards itself in a bond, so it's more electronegative, and the carbon is less electronegative. Perhaps it would look something like this diagram, but this is labeled hydrogen and bromine. But in any case, similar. So they would be sharing an electron, I would say, but not evenly, a polar covalent bond. And over here with lithium and fluorine, a bond between lithium and fluorine, that's very lopsided. For one thing, it includes a metal, lithium, and a nonmetal, fluorine. In my mind, that rule of thumb indicates a salt. So this bond is very, 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 very extremely polar, i.e. ionic. In that case, we say lithium has lost an electron, fluorine has gained an electron, the lithium ion, the fluoride ion. But in any case, this is very, very polar. This is very, very, very not polar, zero polarity, zero lopsidedness, and this is lopsided. So I was supposed to rank them from the least to the most polar. How about chlorine? Chlorine is the least polar, and carbon-oxygen bond is the next most polar, lopsided, and lithium fluoride is very, very lopsided in electronegativity. So not only do the differences in electronegativity count, but also the distances between the two ions. If there's a big distance between the two ions, if for some reason, not necessarily just the bond, then that makes a larger, what we call dipole moment. A dipole moment is some kind of way we can measure the amount of polarity in a molecule. So here's water. Is water lopsided? I would hope you agree that it is. Um, which Roman numeral marks the location of the most electronegative? Well, let's see. In these electrostatic diagrams, red is electronegative and blue is not electronegative, or we could say electropositive. So I'm predicting this to be the oxygen of water and these to be the hydrogens of water. You know about lone pairs? So oxygen has lone pairs on there, on its on the atom, making it very electronegative right over here. So yeah, Roman numeral 2. This one has a dipole moment because it's lopsided geometrically, three-dimensionally in space, and the dipole moment would actually point from here over to here. As a vector, have you had a physics class at all? In any case, what about another one? Let's see. Oh yeah, what about ammonia? Is ammonia a dipole? Is it lopsided? Is it polar? The answers are yes. Since nitrogen is somewhat electronegative, not as much as oxygen, but still it's more electronegative than the hydrogens. Um, it gets a sort of a reddish color, and this side gets kind of a bluish color. And again, the dipole moment would point from the positive to the negative, so it would point from here over to here. In terms of a vector. In terms of predicting the size of the dipole, I would just say it's not as polar as water, because water has an oxygen which is more electronegative, and being more electronegative forces that molecule of water to be more polar than ammonia. But still, ammonia is fairly polar. It dissolves in water really well. Here's 5 molecules. Are any of these five lopsided? Geometrically, three-dimensionally in space. We'll be thinking about this quite a bit later in the beginning of chapter 5. Let's see, the least dipole moment. Which of the molecules is the most polar? Oh, the largest dipole moment. Yes, I can read. So is boron trifluoride, if it's flat and triangle planar, is it a dipole? No. Is carbon dioxide lopsided geometrically three-dimensionally in space? No. Is methane lopsided geometrically three-dimensionally in space? It might look like it, but no. Is sulfur hexafluoride lopsided geometrically physically in space? The answer is this one cancels this one, this one cancels this one, this one cancels this one. No. Is water lopsided geometrically, three-dimensionally in space? Yes. So that's the largest dipole moment. So if it's polar, it has a dipole moment. I could measure it in the lab, but we aren't talking about that right this very minute. We'll never talk about measuring it. I'm just going to say that it's possible to do so. And I can look at the geometry or think about the geometry and say whether or not it has a non-zero dipole moment. Zero dipole moment would mean it's not lopsided. This one has a zero dipole moment. This one cancels this one, this one cancels this one, this one cancels this one. And when I say cancels, I mean something like physics addition of vectors idea. This fluorine pulls in electrons, but so does this one. This fluorine pulls in electrons, but so does this one. This lone pair is very electronegative, but so is this one, and they're all opposite of each other. They all cancel. Did you know xenon can bond sometimes if it's hooked up with someone that really wants electrons, like fluorine? Chlorine tetrachloride, or carbon tetrachloride, just like ammonia, just like methane with CH4 instead of CCl4. This is very non-polar, not lopsided. No dipole moment, no dipole moment here either, because this is not geometrically three-dimensionally lopsided. Same for BF3, just like we looked at BH3 a second ago. I think what did we look at? Whatever, just like that. But this one, this hydrogen sulfide, H2S. Oops. So that one's has the largest dipole moment. All the rest of them actually have a zero dipole moment. If we're asking what's the proper orientation for the direction of the dipole moment, it's usually pointing from the positive to the negative. So if these are H's and this is a sulfur, sulfur is more electronegative than the hydrogens. Oh, is that a fib? I hope it's not a fib. Let's say it is, because sulfur is very close to oxygen. I think it is. Oh, I might be wrong. Well, whatever. So the answer is 2. We would point from the positive side to the negative side. I'll think about that. Oh yeah, so what if we have back to, in most cases, 2 different atoms in a bond? If I have 2 of the same atoms in a bond in a molecule, then it has no difference in electronegativity and no dipole moment. It seems like the greater the difference in electronegativity between the 2 different elements or atoms in the molecule, diatomic molecule, the larger the dipole moment. Lithium fluoride, like I said a little while ago, is so polar, it's like a metal and a non-metal. So I would consider that rather highly ionic in nature, whereas this chlorine, Cl2, is very highly covalent in nature, and these are in between. Let's look at an interesting chart. What if the molecule is more complicated than just 2 atoms or 2 different elements in the bond? Then I need to look at a couple different things. Most importantly probably is just the electronegative regions. If the red in these electrostatic diagrams represents a highly electronegative region, then I would say if it's lopsided geometrically, three-dimensionally in space, isn't this lopsided, as this is more electronegative than this, and this side's more electronegative than that, and this side's more electronegative than that, and this side's a little bit more electronegative if you imagine three-dimensionally than this, and this one doesn't have any big red regions. So I'd say the propane is not very polar. It has a very small dipole moment. This one, stick an oxygen in the middle. That makes it slightly more polar, slightly more polar, slightly more polar, slightly more polar, and this one would have a larger dipole moment. So what? Why do we care about polarity, lopsidedness, dipole moments? If a molecule has a high degree of lopsidedness, if it's very polar, if it has a high dipole moment, then it is more likely to be a liquid, in some cases even a solid at room temperature. But if my molecule has no dipole moment, or very little, then it boils and melts very easily. So this is below room temperature. But here the melting and boiling and the melting and the boiling and the melting and the boiling and the melting and the boiling. Here's a mistake. Well, it's not a mistake. It's an inconsistency in the pattern, but still, you gotta believe me. Overall, the melting and the boiling temperatures increase with increasing dipole moment, with increasing polarity, with increasing lopsidedness. Interesting. Here's another table, similar. Dipole moments, 0.1, 1.3, 1.9, 2.7, 3.9. As I go down this chart, this gets more and more lopsided. So this one's very lopsided, whereas this one's very not lopsided. And this one's in between. That one's more lopsided, more dipole, more polar. This one's more polar. This one's the most polar. Interesting. The boiling point they measured at 231, 248, 249. Wow, that's not much of a difference in boiling point considering the larger difference in dipole moment. But in any case, I can imagine boiling temperatures, but it's more difficult to imagine lopsidedness unless you start to get used to lone pairs and oxygens and electronegativity. I said here briefly, as the molecule increases in dipole moment due to some asymmetry, the interparticle forces, we'll study that more in chapter 8, increase, and that increases the boiling point and the melting point. Again, to summarize, I said if the molecule is diatomic, just two atoms, the greater the difference in electronegativity, the greater the dipole moment. If the dipole moment gets really, really, really big, then we'll just call it an ionic bond. And therefore it's a salt, and therefore it's probably very hard to melt. It's almost likely a solid. If the molecule is large or complicated, we look at the differences in electrostatic potential, if we have that kind of a diagram, or if I know what the atoms are that are more electronegative, like oxygen and fluorine, I can look at those and also consider how far apart those sort of negative and sort of positive, partial negative and partial positive regions are. Large differences in electronegativity and large separations lead to a large dipole moment. And large dipole moments do what? So if I have a very polar molecule with a large dipole moment, it's more likely to be a liquid at room temperature. It melts and boils very hot. It's very sticky and thick. It has a high surface tension, and so it evaporates very slowly. We say it has a low vapor pressure, more of that in chapter 8. And also, it probably would dissolve in water better because water is very polar, and polar things dissolve other polar things. Gotta stop, guys. Thanks for your patience, and thanks for staying awake. My goodness.